Okay, this is a bilging problem where we are bilged at the side, and it's always a midship compartment at the side, so there's no trim involved, it's just simply the angle of list. So I've done a sketch. There's two ways you can look at the sketch. We can look at it forward and aft. There's the length of the vessel, the breadth of the vessel, there's the centre line, and here's our bilge compartment here that we've lost. Or you could look at it this way and say, okay, there's the vessel, that's port and starboard, that's forward and aft, and we've lost this part here. Okay, with bilging problems, the first thing you have to always work out is the sinkage. So it's the volume of lost buoyancy times the area of the intact water plane. So the volume of lost buoyancy, obviously, length of the compartment 24 times 9 times 8.6, which is the draft. The intact water plane is very straightforward. It's the whole water plane, 150 times 28, minus 24 times 9. So if you're looking down from the sky on this sketch, that's what we've lost out of the water plane, minus 24.9. So that gives us our sinkage, and we've got our new draft. We need to find now BB1, in other words, this distance that B has moved. So once we become bilged, B moves off the centre line to its off-centre position, okay, because we've lost this part. And the formula is A times D, or S, sometimes it's called S, over final A, where A is the area of the bilged compartment, D we're going to look at in a minute, and final A is the final area of the intact water plane. So hopefully you can see what we're going to do here. The small a area is 24 times 9. Now the distance is the distance from the centre of the bilge compartment to the centre line, the original centre line. It's 14 metres from the centre line out. This is 9.5, so we subtract 4.5 off that, and that gives us the 9.5. So that's 9, that's 5, making the 14. So another way of looking at it, it's 5 plus half of 9, 4.5, it's 9.5. Or you could just say, well, it's 14 from here to here, subtract half of 9, 4.5. So that's how we arrive at the D value. So the distance B has moved to B1 is 0.515. So from there to there, we've moved 0.515. Now we're looking at inertia, and inertia on the outer edge is LB cubed over 3. And what's happened is we've lost this little bit of inertia here, 24 by 9 cubed over 3. So that's the whole inertia minus the small amount gives us the inertia there. We want the inertia at the centroid or off centre, so we've got to take the inertia from here to here, and it's what we call the parallel axis theorem, where we have the inertia at the side, which we've worked out, minus the water plane area times d squared, and d is the distance from the outer edge to the new centre of buoyancy. So originally it was 14, but we've now got to add b to b1, which is 0.515, so that d will be 14.515. So the inertia at the centroid is the inertia at the side, which we've worked out, minus the area, 3984, times d squared. And d, of course, is, as we've just explained, is 14.515. So that becomes the inertia at our new centroid or off-centre position. Bm is inertia over volume, and remember your volume doesn't change because the displacement doesn't change. We get a Bm of 6.99. Kb is always the draft divided by 2. You don't need to worry about watertight compartments or anything like that. It's always the draft divided by 2. Add the two together and that gives you the Km. Subtract the Kg given, that gives you the Gm. Now we've got both values that we need to work out our angle of heel. So BB1 over GM, it gives us 12.5 degrees. So you just got to be careful when you're working out BB1 what that D is, and then when you're working out your inertia what value you use here for the D squared. So although they're both called D, the different D's, okay? This is the D to do with the bilge compartment to the centre line, and this is to do with the parallel axis theorem, the distance. So they're two completely different distances. Don't get them mixed up.